My name is Tjitske Starkenburg. I'm a research professor at Northwestern University, and I am basically following up on Lucia's talk from yesterday about talking about galaxy physics and dust attenuation in the CAMELS SAM universe. And this is going to be part of my talk, and the other part is a surprise. So, using basically the same layout as Lucia showed yesterday, so it's a little bit of a reminder, this work is done within the Learning the Universe collaboration, and specifically it's called the Connections Project, trying to go through the full pipeline with current methods that we currently have, and just trying to get to some inference results, going from the initial conditions to dark matter density fields, halo formation. In this case, physics-based galaxy formation models, which what I'm talking about is going to be the semi-analytic models from CAMELS SAM. But other options are CAMELS Hydro, and Chris will talk about that tomorrow. Based on those, go to galaxy photometry, or actually build spectra, then go to photometry, build a light cone, do surface-specific observational effects, noise cuts, fiber collisions, etc. Build a mock galaxy survey, compare to the real survey, and do your inference. So, what I'm going to talk about is these two parts, and actually mostly the first part, because as Lucia said, we haven't really gotten to the second part yet. And this work wouldn't be there without Lucia, Austin, and actually I'm also going to talk about Laura's work. And tomorrow, Chris is going to talk about actual results built from the CAMELS Hydro boxes. And all of this is done with synthesizer that Chris will also talk about. So, as Lucia said yesterday, we were still working on getting galaxy photometry working. That has worked, so we have spectra. This is new since yesterday. And so we now have, these are 500 galaxies in one of the, in this case, it's called the fiducial box, new SCSAM model with a new method to save the star formation history is to not run into huge data sets that are not savable anymore for the 100 megaparsec boxes that the SAM has. But we can vary the astrophysical parameters and get different spectra. Unfortunately, this is how far we got for now, but the next step that we need to think about as well and need to implement, will implement, is dust. So if you want to go to observational photometry, dust is a critical component, and it's also very uncertain. So just to remind you, young stars emit in the UV and the optical. That emission can be absorbed by disk range, which is then re-emitted in the infrared. And so the light in the UV and optical is attenuated by dust, and there is dust emission in the infrared. And we need to incorporate that into our models. But we know very little about how much dust, what the composition is, what the distribution of grains is, what the stellar to dust geometry is, and how to implement that in the forward model. So, for example, a few years ago, Cheng and I worked on forward modeling Simba, TNG, and Eagle simulations to an SDSS-like data set. And what we found is that you can get similar distributions in optical color magnitude and UV color magnitude spaces that look very closely to the SDSS distribution, which is in the dashed lines. Except that for all of these models, you end up with different correlations between the galaxy properties and the dust properties that you would expect. And so you absolutely need dust to go from the simulations to observations, which is a good thing because we know dust exists, so we should include it. But the galaxy formation model and the galaxy properties in the simulations are closely related to what dust would optimally get you to the observation. So in a way, there's a degeneracy between how we implement our galaxy formation model and how we implement our dust. And that has been very little explored. You could say, like, okay, so what do? We can't infer anything. Based on that, it's just a problem, and until we know much, much more and can simulate the dust internally and understand it way better, what do we do? On the other hand, I think this is a very interesting tool to actually try to learn more about the galaxy formation models, how that correlates to dust, and that dust to cold gas. So for me, as a galaxy person, it gives me insight into how the galaxy formation models work, and what the physics is that could or should be included there. So Laura Sommavigo and Rachel Cochrane have been working on doing radiative transfer simulations along many, many, many different sightlines for galaxies in the TNG50 simulation and the TNG100 simulation. And so you get pretty images like this. But then what Laura did is to look at what the range of properties are, what the range of the attenuation curves of the dust are that you would get for different sightlines, for different galaxy properties, and how this correlates. And so this is the attenuation curve model that she used, which is in detail not that important, but it has 4 different parameters that vary, which describe the attenuation slope in different parts of the wavelength regime. And you can see that varying these parameters gives you very different attenuation curves. And so what she has shown is that there are correlations between the galaxy properties internally and the values of these parameters. And so you can, she has used that to build a simple, basically a minimal logical model of what correlates with what, and how you could use your galaxy parameters in your simulation to build a simple dust model or a dust attenuation curve for that galaxy. And while we're not going to use that exactly, we can use all of that information to then use that as prior and information on our dust model and on the ranges that we should consider for doing inference, on the regions and correlations that we should consider. So this all is folded into synthesizer or now. And the results Chris will show are not with this yet, but the next step is to both include this model in both the CAMELS SAM photometry and in the CAMELS hydrophotometry, and be able to include this flexible dust model in the full forward modeling pipeline and inference. And so for inference results, I'm letting you wait one more day for Chris's talk. Okay, so then the other thing I wanted to talk about in my last 6 minutes is actually a new AI Astro Institute, which is the NSF Simons AI Institute for the Sky, Sky for short, which is in Chicago, and the major institutions involved are Northwestern, University of Chicago, and the University of Illinois at Urbana-Champaign. But these are not the only institutes. We have a lot of partners in the area, from University of Illinois at Chicago, the Adler Planetarium, Argonne Fermilab, Toyota Institute. Wait. No, I don't remember exactly. Right now, University of Wisconsin-Madison, Toyota Technical Institute for Computation, I think it is. Yeah. But it's a PhD granting institute. And they do a lot of AI. And we have a lot more educational-oriented partners as well, mostly in the region, but also further out. So with all of these, where is this located? So this is a view from Chicago on Lake Michigan. And the Sky Institute is going to be located in that one, which is one of the most well-known skyscrapers in Chicago. It's the Hancock Building. If you do an architectural tour, that's one of the ones that will come up. And we're, oh, wait, go back. And we're going to be on the 35th floor with lake view and city view. just telling you. No, yeah, so yeah, it's going to be centrally located in downtown Chicago, which is very well accessible for everyone. The space is going to be very open with, it's still under construction. Right now, we expect to be able to be in March. We have temporary space also in the building on the 40th floor right now. And we've had our first meeting there last week. So events will start, are expected to start internally in the new year and slowly building up. But expect to see announcements for workshops, conferences, discussions, hacks, slowly building up in the coming year while we build up our research. Because we just got started in October and there is a lot to do. But yeah, one of the things to expect is a yearly conference, which will probably be in the summer. Okay, so what is the research that we focus on? I wouldn't be here if it didn't include some of this. But we go from stars, compact objects, and transients to galaxy formation and evolution and cosmology in the early universe. And so this is on the astro side, but we combine that with, on the AI side, it's pretty broad, but our focus areas are generative models, astrophysics-informed and interpretable architectures, and uncertainty quantification. And so we want to make foundational AI advances, developing new things in all of these areas. And we've combined that in research pillars that actually focus on different parts of the scientific process, of which the first one is enhanced inference from cosmic data surveys. The second is AI-accelerated simulations with multi-scale astrophysics, so simulations that span basically this full range. Not one simulations, but accelerating simulations at all of these different scales. And also learning-based astrophysical survey and instrument design. So survey and instrument design is also a major part of what the Institute will look at. First research projects are expected also to start in January, so I have no results to talk about. But I'm very excited to start closer discussions, and I've seen a lot of people are already talking about possible projects and about starting detailed projects and really combining the astro and AI interest in ensuring that results will be interesting and relevant for both communities and bring both communities forward. That's the goal. And then our overall vision is confront the challenges posed by transformative multi-wavelength and multi-messenger surveys, develop innovative, trustworthy AI tools for the research community, and seed and nurture a diverse generation of interdisciplinary leaders in science and engineering to ethically apply and extend AI within and beyond academia. Very lofty, but what I like is that the Institute includes astrophysicists, foundational AI researchers, but also educators, AI ethicists, software engineers, and also artists. And so there will be artists working based on what the research in the institute is, which is also very interesting to see. And I wanted to leave you with that.
Questions for Tjitske? Paco?
So what is an AI ethicist?
Working on ethics in AI. Yeah. Which is actually a pretty large research area.
Any other questions for Tjitske? If not, I have a question about dust and not about the view. So you showed that equation that looked very, very complicated, which I assume is from PySer, or?
No.
It's not?
No.
That's okay.
No, it's an existing model from, and I should have added the reference. I think it's Lee 2018, which is, there are multiple parameterizations of the attenuation curve, as you know. And this is one that has been used to be fitted to observations. And this is the parameterization that they found the most useful, but basically it's the far UV slope, the near UV slope, the UV bump, and then the more optical and infrared slope. Those are the parameters. But they do interact, so it's not nicely separated, or it's not independent fully in wavelength. But that's basically what the effect is, what they mean.
So in the LTU framework, are like the C1 to C4, are they conditioned on the properties of the galaxy, or do you just allow them to vary?
We allow them. The plan is to allow them to vary. Okay. Currently, yes, but with informed priors based on the ranges found in the galaxy in this work.
I see. Daniel?
Thank you. So related to dust also, so because you mentioned that besides the flexibility in like feedback models that we have, there's a lot of flexibility in the dust aspect, and then just by in the dust, we can make simulations look more similar and match observations better. So I guess just like with feedback models, I guess with dust, then do we want to like marginalize our uncertainties on dust, or is there a hope to like fully predictive like dust models? Any insights?
So there are different goals. So for inferring cosmological parameters in the full LTU connections pipeline, then you'd like to marginalize over dust. But we can also try to infer the dust parameters as well as we can, and then use that both to study what they mean for in the galaxy formation models and how they correlate with galaxy properties and with astrophysical parameters like the feedback parameters. Or if you can infer them separately very well, say on the SCSS main sample, we could use that or use that in a next iteration to then infer the cosmological parameters with a smaller prior, say. So I think there are multiple interests and multiple pathways.
Just a comment. I thought Daniel should mention that Simba has dust, and if you want to like play around and compare with the reference, and feel free to use it, right?
Yeah.
Well, let's thank Tjitske again. Next, we have BK talking about how galaxy properties react to variation in cosmological and astrophysical parameters.
Yep.
Hi everyone, I'm Boon Kiat, or BK in short, and I'm a postdoc working at the University of Connecticut with Daniel and as well as the rest of the CAMELS collaboration. So for a start, my talk wouldn't have any AI. It's just going down to the nitty-gritty details of how the galaxy properties that we see in CAMELS are going to be affected by the cosmological and the astrophysical parameters. So to simplify things, when we look at the galaxy properties, it's basically a competition between the potential, the gravity that's pulling things down, and the feedback from stars and black holes. So it's well known, or it's widely believed, that on the low mass end, the feedback from stars is affecting the stellar formation, and on the high mass end, it's the feedback from the AGNs. And so we have a very simple bathtub model. So the inflow onto the galaxy would form stars, go into the gas, as well as feed the black hole, and then there's some that's outflowing. So feedback is a very complicated process. In one of my previous work, I looked at the zoom simulation. So what I'm trying to do was to calibrate zoom simulation of a Milky Way-sized galaxy on this plane, which is given by the observation from McGaw et al. The purpose is to calibrate the baryon content down to redshift 0. So on the y-axis is basically a measure of the amount of stars that should reside within the halo. And on the x-axis is the amount of gas plus stars, so the baryon content itself. And what we did is, so the color bar that you see here is the one that's given by the observation. So it has a range of values for the M500. And for our simulations, these points here are the range of data that we are trying to achieve. And we did like a one parameter variation that we have in CAMELS. So I varied the star formation efficiency, which is denoted by the green arrow, and the feedback efficiency that's given by the blue arrow. And then the last one is the feedback volume given by the red. So you see from here, this is not a very linear relation. So when you just change, for example, the blue line, the feedback efficiency, it's not linear. So you see at some point it turns around and then it goes in the opposite direction again. So this is very complicated, even just in one galaxy. So what happens now if we were to scale it up to the entire box? Right, so we have different scaling relations that we are familiar with. We have the stellar mass to halo mass relation that you see on the left. And then we also have the coevolution of the black hole mass with the stellar mass that you see on the right, given by the different observations. So we've all heard that the training set, the simulations in CAMELS are very different. So what we see here is like a movie that I've obtained from Paco. So the blue is the gas density and the red is the gas temperature. As you see, when we evolve with time, as time goes on, we see more and more difference that appears between the simulations. And I think this is a good test for us because now we have different models, and that's why there's the need for the CAMELS data. So to go into the details, we have the different parameters, right? So this is a compilation of all the parameters that we have in the 4 simulations that's publicly available: Astrid, Illustrious, TNG, Simba, and Swift Eagle. And they all have similar or different meanings among them, broadly classified into the ASN1, ASN2, AGN1, AGN2 parameters. So even though some of them might appear to be identical, the way they implement it in the simulation is still fundamentally different. One thing to note is, in Swift Eagle, the black hole feedback is only thermal. So as you will see later in some of the scaling relation, that plays a role. So let's start with some of this relation that we are seeing, the stellar to halo mass relation. So it's a lot of things, a lot of lines you see in this plot. And I've tried to explain individual pairs of lines, and I failed terribly. So With this, the different line styles represents the different simulations, and what I'm doing is just taking the minimum variation in the 1P set, the 1 parameter variation, and compare it to the maximum. So in general, although all the parameters, they correspond to different specific details, they all have the sense of increasing feedback, basically. And so I'm trying to try a different way to present this data today with a table. And this is just showing a comparison of what happens when you increase these individual parameters. So as I said earlier, the general idea is increasing the parameter values increases the feedback. So naively, we would think that when you decrease the stellar mass, that should be the expected behavior. So that's labeled as green in the column. And if it was to go the opposite way, it's going to be colored by red, and it's increasing with the stellar mass. And the gray is there's no significant difference. So from this table, again, it's still a lot. So I'm going to classify to the behaving ones. So everyone agrees with each other. So like in this, you see down the column of omega m and ASN2. They behave very well. They agree across all the simulations. And we see this, when we look at the complicated plots again, you see a clear distinction between the blue lines and the red lines, so the difference between the minimum and the maximum value. And some are quite easy to understand, like for example, omega m, when you increase omega m, it decreases the ratio. Likely, I mean, it's probably due to, because we are increasing the dark matter, but we didn't increase the amount of baryons in the simulation. And then ASN2, it's increasing feedback. So, you expect the star formation, the stellar mass to decrease. But we also have misbehaving ones, like for sigma 8, Simba is misbehaving. It's the mass is decreasing, whereas for all the others, the mass is increased. And conversely, for ASN1, the mass is the stellar mass is decreasing as compared to the others. So you see here, I tried to highlight the lines for sigma 8. So on the top panel, top row, it's redshift 0, and on the bottom row, it's the redshift 2. So the reason why we wanted to see it at a different redshift to see if this is evolutionary, if it's just temporary. And we see here also for the dashed line, which is Simba, you see that for sigma 8 at redshift 0, the blue is on top of the red, whereas for all the others, the red is on top of the blue. So when you increase the value, it's increasing the ratio for Simba. So likely it's because of what we've seen earlier, how strong the feedback is in Simba for the AGN. So it's suppressing, so it's affecting the high mass N. So it's counteracting the increase in the clustering. But if we were to look at the ASN1, you see at redshift 0 for Simba, the red line is on top of the blue, but at redshift 2, it's clearly separated. The blue and the reds are clearly different from each other. And so this is probably an evolutionary thing. So it's not permanent. So other properties that we looked at is the star formation rate to stellar mass relation. If you were to look at the table here, again, yeah. So this time round, in terms of cosmological parameters, everyone is agreeing with each other. And if you were to just pick out one that's not agreeing with each other, of course there are others, but for time's sake, I'm just going to pick out one. When we increase the AGN2, it increases the star formation rate in S Street, but Simba and Eagle is decreased to a large extent. So this is the view at redshift 0. Again, complicated. So if we were to look at redshift 2, we see that the same trend persists, and it's likely due to the fact that the difference in the nature, as I was talking about, and how the parameters are now, we are now going to the details, how the parameters are changing different things. So like in S Street, it's changing the energy, whereas in Swift Eagle, for this particular parameter, it's changing both the energy and the frequency. So it has a different impact. And now, if we were to look at the black hole to stellar mass relation, so I forgot to mention for illustration purposes, the gray bands are like observation data that just wanted to plot there and see how our simulation do against the observations. And this is the simplified table that I tried to make. And if you see here for ASN2, Simba, it's the one that's the odd one out. And again, so you see it's very clear for all the other simulations, the blue lines are all below as compared to the red. But for Simba, even though it's not a lot, but it's clear that the blue line is definitely on top of the red. And if you were to look at redshift 2, it's the same. So reason why we think this is the case is because AGN is the dominant form of feedback in Simba, but when you increase ASN2, there's the suppression of the AGN feedback, so which results in the growth in the black hole mass. Right. So we also looked at the stellar metallicity at redshift 0 for the different simulations. Making a simplified comparison, this is much better. Like you see a lot of agreeing colors in each of the columns. But when you look at ASN2, TNG is now the one that's the odd one out. And if you look at this at different redshift, again, this trend persists. And the likely reason is maybe because the baryons are not pushed out as efficiently, so the recycling may have been impacted. And then the last property that we are going to look at is the half mass radius to stellar mass relation. So for all of this in table form, and we look at ASN2, for instance. ASN2 and AGN2. Yeah, we see that for Astrid and Swift Eagle, the half mass radius increases when you increase ASN2, but it decreases the half mass radius in TNG. Again, we think it might be because how efficient the baryons are being pushed. And for the AGN2, it decreases the half mass radius in Astrid, but it increases it in Swift Eagle. So because we didn't look at into specific details, we think that it's because of the nature of the parameter itself. Right, so now we have this exercise for the 1P set, so just 6 parameters. We can extend this to the 28 parameters. So on the left, I'm not going to go into details, I'm just wanting to point out that, so for Simba, we picked out the 9 most influential ones, you see the most variation. And you can see the parameters are dominated by black hole physics. So other than the cosmological parameters that you see on the top, everything else, almost everything else, is the black hole physics. Now, if you were to look at the TNG, so you see a different combination of parameters here. Again, the 9 most influential ones, you see most of them are now sensitive to the stellar physics. So it's a big contrast to what the Simba 28 parameters is showing. So this is not saying that one is right or wrong, but just the sensitivity that they pose to the different formation model. So yeah, so in conclusion, although we increase the value of the astrophysical parameters, and we think that it's increasing the feedback, but they produce very different effects on the scaling relation. At redshift 0 and redshift 2, we see how they change. And one of the things that we see here is you can have comparable effects between the cosmological and astrophysical parameter. So it's difficult to, if I were to just show you the plot, it's difficult to distinguish if it is due to cosmology or due to astrophysics. Hence, we have a need for this large data set so we can do robust inference. Thank you.
Questions for BK?
Okay, can you hear me? I have a question. In the plots, the line red and blue, you were showing the median or the average behavior. I expect that you have a variance also in the simulation.
Yes.
If you look at the variance, you see different effect of cosmological and astrophysical parameter. Can this help in characterizing the effect of the two kind of parameter?
Oh yeah, definitely. But yeah, in the plots itself, it's just the median. So within each bin, we take the median. Yeah.
But you did look also at the variance.
Yeah, we can. Yes.
Okay, can you say something on this?
I don't remember off the top of my head, but yeah, I mean, we can chat later. Thanks.
Any other questions? Chris?
Yeah, really interesting stuff. Have you looked at any of these, say, CV or 1P sets at individual galaxies and the differences there, as well as the scaling relation?
Not yet, but we are doing a test like for the 50, but not like for the 50 megaparsec TNG, like comparing 25 versus 50, but individual galaxies, like to match them, no, not yet. Yeah.
If there's not any questions, I haven't one. So this is, you're doing God's work here, chasing after the reason behind the effect of all of these different parameters. I'm curious whether all of this comparison has shed some light on the actual physics that goes in. And I mean, you had some figures where you plotted with the observational constraints, and there were some cases where among the lines it seemed like even between, it wasn't even between the min and max. So is there any insights on which prescriptions you think should be ruled out? I mean, let's name some names.
Well, we are not going to rule out anything, but hopefully it can help explain some of the results. Like, for example, Erwin presented on the first day. He had some weird, unexplainable results when he changed certain parameters. So we were thinking, maybe if we were to look at these relations, it can help him explain some of the results, as well as, other people who have looked at when they change parameters, they see some weird results. Maybe in one of the columns, in one of the plots, they can potentially explain why they are witnessing such results. But to rule out, no, not yet.
That's a nice diplomatic answer. Any other questions for BK? Otherwise, let's give her another round of applause.
Thank you.
And don't go to coffee break yet. Shai has some announcements.
Hi again, everyone. So I'm going to do some shameless advertising, and I'm going to shamelessly stand between you and your food while doing it. So we just wanted to highlight a few programs that we have at CCA that people are kind of new and people may not be aware of, and kind of target different audiences. So I want to go quickly through this. So we have the usual, what we call the Flatiron Research Fellow program, which is our postdocs. It's too late for this cycle, but we do this every year. You may be aware of that. But a newer edition, which I think this year we've advertised for the third time, but yeah, we're going to keep doing this every year, is the Flatiron Software Research Fellow program. So these are 5-year postdoc positions, which are really based and driven by development of scientific, astrophysical software. So, if you're interested, if you feel like what is really driving your science and your interest is software, there is this type of position. They're kind of longer than the standard 3-year positions, recognizing that it takes time to develop software and get the scientific fruits out of it sometimes. So that's that. So that's advertised on WAS every year now, along with the usual postdoc program. Then we have the pre-doctoral program. So that's a program for PhD students to come here to spend 5 months working with an advisor from our staff. The idea is to, expose the students to a different group of people, different mentors that work. The idea is for them to work on something that's kind of related to their thesis, but not something that they would do normally in their home institution. So kind of add another chapter to their thesis or something like that. We have 1 call per year in the spring for 2 classes, the fall class and the winter class, each one. So September to January, January to June. So particularly the students, and the advisors also encourage your students to do this. Then I'd like to advertise our sabbatical program or long-term visiting program. That's, I believe, on the AAS. You can find the ad. The deadline is pretty soon, January 2nd. I just want to highlight that this is a very, very flexible program, so you don't have to think about it as like a full year sabbatical. It could be a half year sabbatical. It could be like 2 1 month long visits. The application is very simple, kind of up to 2 pages. General, what would you do here? Who would you interact with here? And finally, we are doing a search for a new hire at the kind of research scientists level, so that's long-term position. We're doing open rank, so we're open to senior positions as well as positions at the kind of junior faculty level. So it's a pretty open search, but we did specify kind of 5 focus areas of interest, 3 of which are very relevant for this audience, so cosmological surveys, the CMB, machine learning for astro, and statistical techniques for astro. So deadline is also pretty soon. That's also on the AAS. So if you're interested, consider applying or letting your relevant colleagues know about this. Any questions before lunch? I think it's sometime in the spring. I think so. I don't think we have a set date for it right now, but I think typically it's been maybe the call comes out in February or March, deadline in April, decisions in May, so something like that. So just be on the lookout.